All right, up to this point, we have pretty much assumed that atoms are neutrally charged. That is, that the positively charged protons and the negatively charged electrons in the atom are close enough together that from the outside of the atom, it seems like it's uncharged. All that positive charge cancels with the negative charge, so we say that that cancellation makes it neutral. It neutralizes that charge. So it seems like it's not charged at all, even though the protons are still positively charged and the electrons are still negatively charged. So if we go and mess with that balance, that cancellation of the positive and negative charge by changing the number of electrons, we should end up with an atom that does have some total charge left over that's not canceled. We call that the net charge of the atom. Whenever we wind up with an atom that has charge, we call that an ion. So we're going to be looking at how we form ions today. Oh, hold on. Get that out of there. Charged atom. That's all an ion is. It's a charged atom. Okay, so just because something is neutral and cancels out all that positive and negative charge doesn't mean that that's the most stable form of that atom. We can actually make the electron cloud and the atom overall a little more stable based on how we maybe gain or lose electrons. So we'll be looking at that. And we'll also look at kind of a shortcut to figure out, well, am I going to gain electrons or lose electrons, and how many? A guideline more than a rule. We tend to call it the octet rule. Okay, so let's look at how we form ions. We're going to use fluorine as an example first. Okay, so fluorine, if we go look it up on the periodic table, has 9 total electrons as a neutral atom. Okay, it's in the p block, so that means it ends in a p orbital. It's in the second row of the periodic table, so it ends in a second energy level orbital. So let's see, it is 1, 2, 3, 4, 5. It is 5 columns into the p block, so it ends at a p5. Second energy level, so 2 p5. So we have to fill up every orbital up through 2 p5, and then we stop there. So it's going to be something like this: 1s2, 2s2, 2p5. Okay, so that's how fluorine usually is as a neutral atom. Okay, now valence electrons are the number of electrons farthest out in the electron cloud. In this case, our second energy level is the farthest out, and we have 2 electrons in the 2s and 5 electrons in the 2p. So in the second energy level, we have a total of 7 valence electrons. Now, just to double check this, there should be a little bit of a shortcut with how many valence electrons an atom has, starting with as a neutral atom, compared to where it is on the periodic table. Fluorine is in column 17. So if you kind of ignore the 1, it should have 7 valence electrons, which it does, which is nice. Okay. So if I wanted to jump straight to it and I didn't need to write out the electron configuration here, I could tell that fluorine has 7 valence electrons based on its group number, its column number. A group just means a column going up and down. Okay. So if I were to draw a Lewis dot diagram for a neutral atom of fluorine, I'd put an F here. That's my fluorine. Okay, and I'm going to give it 7 dots for its 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7 valence electrons there. And again, it doesn't really matter how you organize those around. You know, you could do it instead. You know, like 1 here, you know, and maybe your odd one out is over here. That's fine. We tend to spread them out as much as we can before we pair them up, just like we do in orbitals. But as far as where that leftover electron is, that unpaired electron there, it doesn't really matter where you leave it. in this case. Okay, so what we need to figure out is how fluorine is going to feel better than how it is right now as a neutral atom. Okay, if it's going to become an ion, it's going to either gain or lose electrons, and supposedly that should help it, feel better somehow. So what we could do is look at the periodic table and figure out what atom or what element close to fluorine is kind of a role model for it. It's an icon. It's like the cool kid on the block. Well, most of the cool kids in terms of elements on the periodic table hang out in column 18. We call them the noble gases because they're kind of like the royalty of the periodic table. They are especially stable. They don't go making bonds. They don't need to hang out with other atoms. They don't participate in reactions very often. They're kind of too cool for everything. They're just kind of like, I'm going to be on my own. I'm a loner, lone wolf type. So, I don't need all that other social stuff. I just kind of want to be on my own the way I am because I'm perfect the way I am. Maybe a little snooty, but they do what they do. So other elements can look at the noble gases in column 18 all the way on the very right of the periodic table as kind of like, I kind of want to be like that. And they kind of want to, pick up the same fashion, wear the same shoes, kind of follow the same trends. They want to kind of mimic the noble gases. And they do so by trying to get the same number of valence electrons. Or better yet, get the same electron configuration as a noble gas, as something in that column 18. So being in column 17, fluorine is already pretty close to one of these elements. In this case, if you look all the way over on the right side of the periodic table, neon is pretty darn close. So neon is a noble gas that's right next to fluorine. We have something like this. It's like fluorine is here. It's got atomic number 9. You've got neon right next to it. It's got atomic number of 10. Something like that. They're like right next to each other. So if fluorine wanted to have an electron configuration like neon, well, neon ends in 2p6. Okay, so neon's electron configuration, let's do this in another color, is 1s2, 2s2, 2p6. So if fluorine wanted to be just like that and have 2p6 where it ends instead of 2p5, it's missing an electron. Okay, so if it wanted to be like neon and kind of mimic neon, to be like a noble gas, to have that same electron configuration, it needs one more electron. So what is fluorine going to do? It is going to go find an electron somewhere. It's going to grab it from something if it needs to. Okay, fluorine is just like, I am so close to being like neon. All I need is this one last thing. I just win one more electron and I'll be like that. Okay, so fluorine is going to try to gain one electron to become more stable. Okay, to be like neon, which is very stable. Okay, now does fluorine change into neon? No, we know from nuclear chemistry that that would require a change in protons. We're not changing protons, we're just changing electrons. So fluorine is still fluorine, but it has now gained an extra electron, which means its charge is changing and it's no longer neutral. So what we've made is an ion. Okay, so fluorine has now picked up one extra electron here. Okay, we started at a charge of 0. We gain an electron, which means we are adding one on here. Okay, an electron is negatively charged. So we're adding a -1 charge to this atom. So if I take 0 plus -1, that gets me a total charge of -1. Okay, so this atom has a net charge of -1 when it picks up an extra electron and becomes an ion. Okay, so having that negative charge is what makes this thing an ion. Okay, now an atom could be positively charged or negatively charged to become an ion. So to be more specific, we have names for which kind of ion is which. In this case, a negative ion is called an anion. It's a negative ion. All right, kind of looks like anion, like someone misspelled onions, but it's anion. The ion part in there is kind of the key part there. It is an ion, specifically, it's negative, so we call it an anion. Okay, so by picking up an extra electron, fluorine goes from having 7 valence electrons to having 1 more. All right, so it's going to wind up with 8 valence electrons. And what do you know? Neon also has 8 valence electrons. It goes up to 2s2, 2p6. So it's got an electron configuration just like neon now. Again, still fluorine, still the same fluorine we know and love. Okay, but now it's got the electron configuration to match a noble gas. And that makes it more stable. It's acting just like an element that is stable due to its electron configuration. Now, fluorine is a little different now, so we should probably update its Lewis dot diagram. So let's scroll down a little bit here. Okay. So I'm going to do it off to the side so I have some more room. So here's fluorine. And it had its 1, 2, 3, 4, 5, 6, 7 valence electrons here. And it picked up an extra one. Okay, cool. Well, that's not the only thing that changed. It now has 8 valence electrons, but it also has a charge. So we should probably show that on the Lewis dot diagram too. Okay, to show that negative charge, we're going to do a little negative sign like this. Okay, just put a little negative sign up by the Lewis dot diagram. Usually it's up in the top right. It's just kind of the tradition, the convention for it. Okay, so our atom now has the electron configuration similar to neon, Ne. Okay. And now we're going to find a similar trend with a lot of different elements, that a lot of them will try to be like a noble gas by gaining or losing electrons. So they follow kind of this same sort of trend. Now, if you look at group 18, where all the noble gases are on the far right of the periodic table, they all end in a P6, like a 2p6, a 3p6, a 4p6, or something like that. Almost all of them do, at least. There's a caveat there. We'll come back to that. Most of them end in a P6. Well, the d orbitals and f orbitals don't show up as valence electrons because they usually get filled as we fall back in to kind of the inside of the electron cloud. We call those the core electrons. So we only ever see s electrons and p electrons as valence electrons. As a result, we end up with kind of a full energy level, or a full set of kind of valence orbitals, sometimes also called a shell, when we have a full set of s orbitals and p orbitals farthest out from the nucleus in the valence energy level. Okay, so if we have 2 electrons from the s orbital and 6 electrons from p orbital, whether we're in the 3rd energy level or the 4th or the 5th or the 6th or whatever, we're going to often see an element stabilizing by reaching 8 valence electrons. So octet stands for 8. And specifically, we're trying to get 8 valence electrons. I'm going to do VE for valence electrons. And remember, a valence electron is no different than any other kind of electron. It's just an electron that's farther out in the nucleus, or in the electron cloud. Okay, so an ion of this element ends up with 8 valence electrons, so it follows the octet rule. It has 8 valence electrons. That's all you really need to achieve to follow the octet rule. So this element does follow the octet rule. Okay, so that's an example of making a negative ion, an anion, like what fluorine does to be like neon's electron configuration. That's not the only way we can make ions, so let's look at another example. Next up is sodium. All right. Well, let's look at sodium's electron configuration. It ends at 3s1. All right, it's got a total of 11 electrons. So it looks something like this. 1s2, 2s2, 2p6, 3s1. Okay? So a neutral atom of this element has how many valence electrons? Well, its farthest out energy level is the third energy level. And it only has one electron in that s orbital there. So sodium only has one valence electron. Okay, now we can double check that kind of shortcut, that sort of little cheating method to see how many valence electrons we have. Okay, sodium is in group number 1. It's in column 1 of the periodic table. So yeah, it's got one valence electron. That kind of matches. Don't need to knock off a tens place or anything like that. If I wanted to draw out the Lewis dot diagram for sodium, it would be Na, that's sodium symbol. It's one of those weird ones. It has one valence electron, so I'm just going to give it one dot, like that. Okay. So if I were following along the same lines as fluorine, I might say, well, okay, I want to get electrons to look like one of the noble gases, okay, one of the column 18 elements. Okay, that's all the way across the other side of the periodic table on the right side. Sodium's on the very left. Okay, so if I were looking in the third row of the periodic table, and I was like, okay, well, sodium can gain electrons to be like argon all the way on the right side. That's a lot of electrons. It's only got one valence electron right now. Argon ends at 3p6. That's a little rough. We'd have to gain like 7 electrons to get there. Okay, in order to get to be like 3s2. Let's do this. Argon. 3s2, 3p6. That's a lot. It's not likely that our atom is going to go around and forage for 7 electrons from somewhere and just grab all of them. That's a lot of work. And remember, the goal here is to stabilize. Okay, if our atom has to put in a lot of work to go find a whole bunch of electrons, that's not going to make it more stable. It's going to be way more work than it's worth. So that's probably not our best option. So maybe we aren't always going to gain electrons to make an atom more stable. Well, what option does that leave us? What if we lost electrons? Well, sodium really only has one valence electron to lose. So let's say we lost that one. Okay, what would that leave us at? If we lost that one valence electron, its electron configuration would be 1s2, 2s2, 2p6. Well, that looks kind of familiar. 1s2, 2s2, 2p6 is the electron configuration of neon, which is in column 18. It's a nice, stable, noble gas. So we kind of still got there. But losing one valence electron is way easier than gaining 7. So this is probably going to be the better way to do it. Interesting. So if we end up losing one valence electron, do VE again for valence electron, we could still wind up with the electron configuration of something in column 18, one of those very stable, noble gases. It just happens to be that we go backwards on the periodic table instead of moving forwards. So, like neon is right here, and it's got its whole, oh, sorry, not neon, sodium. Got too many things with N's. So sodium is here. And it's got magnesium next to it. It's got a whole bunch of space. And then you have the P block over there. Okay, but rather than trying to go through all that, if we back up, we can reach neon over here. Now, this isn't a great depiction of the periodic table, but you get the idea. So that gap should be bigger. But we go backwards. That's the point I'm trying to get to. We lose one valence electron, and we still wind up at group 18, at column 18. Okay, in this case, we're looking at neon's electron configuration, which is kind of crazy. Okay, so we still achieve that more stable electron configuration. It's just in this case, we lost that one electron, so let's see where that takes us. All right. We started with a charge of 0, a neutral atom of sodium. This time, we lost an electron. So to show that, I'm going to subtract. I'm going to lose one electron, and each electron has a -1 charge. So I'm subtracting -1 charge. What does that leave me with? Well, 0 minus -1 is going to give me +1. So sodium as an ion is going to have a +1 charge. Okay, so we can't call this an anion if it's positively charged. Instead, it's going to be a cation. Okay, so how many valence electrons is sodium going to have after all is said and done? Well, I'm going to kind of answer this question here by drawing out our Lewis dot diagram and kind of helping us out with that. So this is kind of the easy jump to answer. Here's my sodium. I used to have 1 dot for 1 valence electron, and now I don't. So maybe that's all I write, just Na, no dots. And that's the way we see it a lot of times in chemistry. We lose that 1 valence electron, so it has no valence electrons. We can show its charge. It's positively charged, so I can put a little plus up in the top right, just like that. Okay, and that's my Lewis dot diagram. But this isn't the only way you might see it. This other way is not as common because it can look a little confusing. But it's going to help us answer this question here. How many valence electrons does sodium have? Okay, we know there's a question down here that's going to ask us, does this follow the octet rule? Well, in order to follow the octet rule, it's got to have 8 valence electrons, just like neon did. I mean, we are like neon now. We wound up with neon's electron configuration. Since we lost that 1 electron in the 3s orbital, we don't have any electrons in the 3s energy level anymore, which means that's not where our valence electrons are anymore. Instead, our valence energy level is now right here in the second energy level, where we have the 2s2 and the 2p6. Well, guess how many electrons we have there? 2 in the 2s, 6 in the 2p, for a total of 8 valence electrons. So we might not show it this way because it gets a little cluttered and it might send the wrong idea about whether something is gaining or losing electrons. But really and truly, sodium has 8 valence electrons when it becomes an ion, which is kind of crazy. So one way you could show this is to make your Lewis dot diagram like this. Na, and we're going to have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And we can put a little positive sign up there in the corner, again, to show it's an ion. All right? So, again, chemists tend not to do it this way for partially reasons of laziness. We don't want to draw on all those dots if we don't have to. And also to be clear about what's happening to make that an ion. Now, a chemist should be able to look at the positive charge and say, okay, well, this lost negatively charged electrons, but at first sight, it might also be confusing. This might look like suddenly sodium is gaining 7 electrons, which isn't what's happening, and we're showing that with the charge. So we will oftentimes see this in chemistry, okay? But this might help you understand why we have 8 valence electrons in an atom of sodium, and why this does follow the octet rule. Okay, so our sodium follows the octet rule. It ends up with 8 valence electrons, so it still is a very valid way to make the atom more stable. Okay, so an atom can gain or lose electrons to become more stable. Okay, as long as we end up with an electron configuration like one of those guys in column 18. Let's look at some other examples that are a little bit harder. And all through this, I'm always a huge fan of making things easier if we can. So we're going to have a little bit of a shortcut here. Okay, the octet rule tells us that kind of the golden number of valence electrons that an atom should have to be very stable, to be like something in the noble gas column in column 18, is 8 valence electrons. Okay, whether you're ending in 3p6 or 4p6 or 5p6 or whatever, 8 valence electrons is a great number to end in. Okay, so what we could do is say, what is the quickest path to getting 8 valence electrons? Either gaining electrons or losing electrons. So what I've got here is basically just a scale. 8 valence electrons on the top, 0 on the bottom. Okay, now we know that if we end up with a 0 valence electrons, that actually isn't really 0, since we get the number of valence electrons from the previous ending row. All right, so 0 valence electrons means the energy level underneath is going to have an S2 and a P6 now as the valence energy level. So that's also actually 8, which is kind of nice. Okay, so our goal here is to either, let's change to this, to either gain electrons to get to 8 valence electrons or lose electrons to get to 8 valence electrons. Okay, so let's try and figure out what's best here for oxygen. Okay, oxygen, okay, has an electron configuration kind of similar to fluorine. All right, it's pretty close. It's like right next to it. It's like right here. A total of 8 valence electrons. So if we check where it's at on the periodic table, it's in column 16. So our shortcut tells us it should have 6 valence electrons. And just to kind of confirm that, its electron configuration is 1s2, 2s2. It ends in 2p4. So the second energy level is farthest out. A little bit out. Oh, too far. Too close. Okay, we'll deal with that. 2 electrons there, 4 electrons there, for the total of 6 valence electrons. So nice. So oxygen starts with 6 valence electrons. We could draw out its Lewis dot diagram by making a big O right there and giving it 6 dots. 1, 2, 3, 4, 5, 6. 6 valence electrons right there. Paired up 2 of them, 2 sets. Okay, so if oxygen is starting with 6 valence electrons right here, would it be easier to lose electrons, okay, which in this case would mean losing 6 valence electrons, or gaining electrons, which would be just gaining 2 to get to 8? Well, pretty obvious. Oxygen is just going to gain 2 valence electrons to get to 8. Okay, way easier than losing 6. All right, we're taking the path of least resistance. So oxygen is going to gain electrons, and specifically it's going to gain 2 electrons. Well, if oxygen starts with a charge of 0, a neutral atom, and then gains, so adds, 2 electrons that each have a -1 charge, it's going to be adding on -2 charge. So 0 plus -2 gives us a charge of -2. Okay, so we end up with a negative ion. That means this is an anion. All right. And when it gains 2 valence electrons, it winds up with 8 valence electrons, which is a pretty good sign that this is going to become more stable. Okay, so our new Lewis dot diagram might look something like this. 1, 2, 3, 4, 5, 6, 7, 8. We end up with 8 valence electrons. Okay, and it has a -2 charge. Now, this is something that's going to be a little bit weird. We want to show that it's negative. Okay, so we're going to end up with a negative sign here, but we have to show how negative it is, which means we need a number there. Okay, now in chemistry, if you had a -2 charge, historically the way this was done was doing this, negative, negative. Well, okay, I guess there's 2 negative charges there. I get it, but that's kind of sloppy, and it's just not the best way to do it. But they're still kind of stuck on this convention. So rather than writing, you have a -2 charge, since they had a negative, negative, they wanted to be like, well, that means that you have 2 negatives. So it looks weird. It looks backwards. It should be like -2, like we write the charge like that, like like a real negative number. But it's not. We end up writing it with the 2 first and then the negative number, the negative sign. So it looks kind of odd, looks kind of backwards. But this is how we do it in chemistry, and so we'll deal with it. Okay? So oxygen then has an electron configuration that is like neon, since we just added 2 valence electrons. It's moving 2 spots over on the periodic table to the right. Or you can think of it like adding 2 valence electrons here makes it 2p6, which is neon's electron configuration. There's a couple ways you can go about it. Okay? Either way, though, we are now looking at the electron configuration of neon. Oops. Neon. Okay? It's still oxygen, but it's mimicking the electron configuration by having neon's electron configuration. So it's going to be more stable to be like stable neon. Okay? Since it ends up with 8 valence electrons, this does follow the octet rule. Okay. This last example, I'll kind of leave for you to figure out, but I'll kind of set it up with you. So let's make my scale again so we can kind of have that shortcut. So that's 8, 7, 6, 5, 4, 3, 2, 1, 0, which is actually 8. Again, because we back up to a new set of valence electrons closer into the nucleus. 7, 6, 5, 4, 3, 2, 1. Here we go. All right. Aluminum is in group number 13 on the periodic table, kind of like right after the D block in the 3rd row of the periodic table. Actually, let me change colors here. So this was our number of valence electrons. All right. Aluminum is in group 13. So it should have 3 valence electrons. Just to double check it, let's write out its electron configuration. It ends at, let's see, 3rd row, and that's right at the beginning of the p blocks. It should end in 3p1. So its electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p1. Well, what's our farthest out energy level? That's the 3rd energy level. We have 2 electrons in the 3s, 1 electron in the 3p, for a total of 3 valence electrons. Nice. All right. So I could draw out aluminum's Lewis dot diagram by giving it 3 electrons. Cool. So if aluminum is starting with 3 valence electrons here, what is it going to do? Is it going to try and gain 5 electrons or lose 3 electrons? Which is going to be easier? Okay, and think about this. If it's gaining or losing electrons, okay, be careful what's its charge going to be and what are we going to call it? Remember, cations are positive and anions are negative. Okay, so would it be easier for aluminum to lose 3 electrons or gain 5 electrons? Based on that, how negative or how positive does it become based on how many electrons it gains or loses? What noble gas is it going to kind of be like once it gains or loses those electrons? And does it follow the octet rule? Do we wind up with 8 valence electrons, either by gaining or losing? Okay, so give that one a try for yourself.